Okay, so welcome back to the third lecture. So I'm going to talk about demographics, automation, and the future of work. The future of work is something we've talked about a little bit, but I want to come back to it at the end of this lecture. But I'm going to start with demographics. This is no news to people in Finland, because it's a country that's undergoing rapid demographic change, but it's not unique to Finland, as you also very well know. The world is aging, and in particular, the developed world is aging. So here, what I'm showing is what's going on in all countries in the world. This is the OECD. The OECD is older than all of the countries because it's older than the developing world, but actually it's only slightly faster than the rest of the world. So even Africa, which is one of the youngest continents, is actually going to age quite significantly over the next 30 years. I'm showing it here up to 2025, but this pattern continues. And forecasts are fairly accurate here because they're based on current and past fertility rates. This is the US. As you'll see, actually, the US has aged much more slowly than the rest of the world up to now, about now. It's going to start aging also. But these are the two other countries that I want to highlight, South Korea and Germany. Japan is also in the same boat, but I didn't want to put that here also. Germany started aging much earlier than many other developed economies, and it's been aging very rapidly. So you see a very rapid aging here. And this is South Korea, which started out younger, but has aged and actually also taken off, become as old as any other OECD country, the average OECD country over this time period. So you can use many different measures of aging. Here, for theory-related reasons, I'm focusing for the ratio of older to middle-aged workers. So these are the population above 55 to those between 55 and 25, but average age or other cohort sizes also behaves similarly. This is a pattern that has started generating a lot of attention and about time, because I think its implications for the world economically and socially are just completely sweeping. But the attention has almost completely been on the economic front, on the costs of aging. So some ideas, many different names could be put here, so I've been a little bit arbitrary, but demand side concerns that were first expressed by Alvin Hansen is that an aging world will create special macroeconomic problems because there will be more saving and not enough demand for investment, and that's going to create huge macroeconomic problems. And some people see the very low interest rates as an outcome of this sort of thing. Almost everybody who works on this thinks that this is an ominous sign for the future, and the most extreme views would be sort of structural unemployment or structural stagnation being one side. But supply side, or those related to potential GDP, are even more straightforward to think about. They were emphasized by Gordon's recent book, for example, but we know several things. Older workers drop out of the labor force. Even when they don't drop out, they're lower productivity. So if you look at I didn't bring this figure, but if you look at the wage pattern of American workers, for example, they peak somewhere in the 40s and then start declining. So people interpret that as being lower productivity for older workers. If you look at entrepreneurship rates, they're much lower among older workers, so older cohorts may generate less innovation. So there are a range of issues that people worry about. But perhaps most ominously, as we are already experiencing in Japan, or Japan is experiencing, I'm not experiencing, but Japan is experiencing, this creates a shortage of workers, which then leads to a variety of other problems, especially for critical things, both from manufacturing to services. So, in light of all of these concerns, you would expect that there should be plenty of evidence showing that aging has been associated with really bad outcomes. But since a lot of this is in macro, and in macro sometimes people forget to look at the data, so I looked at the data instead. And here is the data. This is a striking, I will claim anyway, this is mine, but it's a striking picture given how much has been written in macro about the terrible things that aging does. On the horizontal axis, ratio of older workers. You can use any measure of aging you want here, any demographic change variable. And on the vertical axis, change in GDP from 1990 to 2015. So 1990 because that's the period where aging really starts being a major issue for most countries. The diamonds are OECD countries, the circles are other non-OECD countries. There is absolutely no relationship between aging and GDP growth. And you can do anything to this data, there's no way you can find a negative relationship. So aging countries are simply not growing more slowly. So for many, many theories that people have advanced, I would say this is a major puzzle. For structural stagnation, for supply side reasons, there should be a negative relationship. Where is it? Why is it that Germany, which is here, Korea, this is Germany here, where is Germany? Somewhere here. Those countries should be doing much worse than, say, the UK or the US or India or Latin America, where aging is not as rapid. Within Latin America, within Europe, you should see the same pattern, and none of it is there. Why not? I don't know. But even though I don't know, I won't stop speculating. And here is the speculation. It's that automation has been undoing the effects of aging. So what I'm going to show you today, or this lecture, is that aging creates the lack of a particular type of labor, and that particular type of labor is exactly the one that robots replace, or other types of automation technology. So I'll talk about other types of automation technologies as well as robots. And in fact, this is the reason why, as I said in the previous lecture, US is actually a laggard. How come US is a laggard in one of the most promising technologies of the age, when we already think of them as technological frontier, especially in digital technologies? How far behind they are. So number of industrial robots per 1,000 workers in the US is 9. That's 14 in Japan, 17 in Germany, 20 in South Korea. If you look at the major 15 robot producers in the world, only one of them is in the US. 7 are in Germany, 7 are in Japan. So US is a real laggard, and it's actually true in other automation technologies too, as I will show you. And that's partly because of aging. So this is the same picture, and these are the same patterns. So the robot adoption, this on the right-hand side, follows. You see Germany, you see South Korea. When it has this inflection in terms of aging, it quickly has an inflection in terms of robot adoption. So what I will argue in detail is that this is theoretically what we should expect. So now I'm going to endogenous technology. So going back to the questions on directed technological change, and this is why I refrain from doing much more of it in the first lecture. I will show that aging leads to greater development of adoption of robots. I will show that the effects of aging are going to be more pronounced in some industries. And I will also show what the productivity effects are going to be. Then I will show several, at least to me, very interesting empirical patterns. First, I'm going to show you, you might not have known this. I don't think, labor economists didn't know this. It's interesting. That actually there is a very, very steep age pattern across occupations. So blue collar production work completely drops off after 50. And it is those younger middle-aged workers, 30s, 40s, that are becoming very scarce in aging countries. And I will also show you that robots replace exactly those workers. And I will show you that both with quantity data and price data. And then I will use several sources of data on not just robots, but many other automation technologies, both cross countries and within the US, that aging leads to a very large increase in automation. And then I will try to bring everything back and discuss future of work in light of this. So since there are many different parts of this particular lecture, here is a roadmap. So I'll go a little bit about the theory. Some of it will replicate, so I'll go very fast on things that we have seen already, but then the directed technology part is new. I'll be fast on data sources, some new data sources, which might be useful for those interested in robots. And then I'll spend quite a bit of time on US data showing who works in what industries and what robots do at the micro level, and then I will show you the results of cross-country, cross-industry, cross-commuting zone results. The model is very similar to what I have done so far, but with some differences. So again, we have many industries, no local economies now, many industries, sigma elasticity of substitution. But now each industry uses production tasks and service tasks. So alpha I is the share of production tasks, 1 minus alpha I is the share of service tasks. So if you look at education services, this 1 minus alpha I is very small. If you look at automotive, alpha I is very large. The production tasks are done by combining tasks. And here I'm assuming that they are combined with a Cobb-Douglas. Again, in the first lecture I did general elasticity of substitution. It doesn't matter. It's just tractable here to do it. And I'm going to assume that these tasks, these production tasks, are going to be done by either middle-aged workers or machines. So that's a very stark assumption. Of course, in general, there's an age gradient, and I'll show you in the data there's an age gradient, but I will also show you in the data that it's very sharp. So it's not a crazy assumption. A better assumption would be an assignment model, but that gets more complicated, so I'm not going to do that. So this is exactly what we did before. Tasks above theta I are not automated. They're done by labor, IZ, because task Z, industry I. Tasks between Z and theta I and industry I are automated, and now I killed all those gamma terms, which were the comparative advantage, so one robot does one task, just for simplicity. So the occupational structure is like this. There's 1 minus alpha I support service tasks. Those are done by people who are wearing ties. They could be men or women, so it's not gender specific, but you have to wear a tie. And then these production tasks, they're done by machines or by people, and here you cannot wear a tie. Those are the blue collar workers. Okay. So in particular, there's going to be machines with some rental price. There's going to be middle-aged workers, and their supply is L, and their wage is going to be W. And there are going to be older workers, their supply is S, and their wage is V. So the sharp assumptions I have made to simplify things imply that these older workers, where did I go? These older workers are going to do this thing. What about the middle-aged workers that are going to do this XI, but they are only going to do these XI here, because those ones are taken by machines. So this specification already makes it apparent, some details we'll see, that machines compete with these production workers. We already saw evidence for that in the previous lecture, but also that it's going to compete and it's going to be highly substitutable for the workers performing those tasks, which are the middle-aged workers. And they're going to be implicitly complementary to the support tasks. So let me actually summarize the result there without going into too much detail, because it's very similar, except slightly more elaborate than what I've shown before. But the key thing I'm going to condition on is phi, which is the relative supply of older workers. So that's S over S plus L. That's very similar to my aging measure. My aging measure is S over L, but in the theory, S over S plus L is slightly cleaner. And then capital theta, which is the vector or sequence of automation threshold. So that summarizes how much automation there is in different industries. So given phi and theta, there exists a unique equilibrium. And in this case, it will be useful for you just to get a slight intuition to represent the equilibrium in a diagram. So here we have V, the wage of older workers, W, the wage of middle-aged workers. These curves are the ISO cost curves. So this is the combination of W and V that would give you that the cost of a final output when you combine all industries is equal to 1. That's going to be our numeraire. So this is like the numeraire condition along the equilibrium path. And this dotted line is exactly my aging measure, phi over 1 minus phi. So the place where these things are tangential, initially this red dot, is the equilibrium. So that's what an equilibrium is. So what happens if there is aging? If there is aging, we go to a steeper line. So aging makes the middle-aged workers scarce, therefore their wages increase, and it makes the older workers more abundant. Just think of Japan, and that makes their relative wage go down. But automation has very different effects. So automation now is the displacement of workers. And the way that the displacement effect, again, this is general, but in this context it makes it bears repeating. What is a displacement effect is that now we are moving along because this ISO cost curve becomes steeper. Why does it become steeper? Well, because we are substituting machines for middle-aged workers. We don't need as many middle-aged workers. So therefore, the displacement effect is simply how we move along this new ISO cost curve that goes through the same initial equilibrium point. So the displacement effect then reduces the wages of the middle-aged workers and increases the wages of service workers or the older workers. Why is that? Well, because the displacement effect, remember, always reduces the demand for the workers that are being replaced. And now the workers that are being replaced are the production workers that are middle-aged. So that's the displacement effect. But now that's complementary to the rest of the production process, which are the non-production tasks, planning, management, design, back office work, and so on. AI might change this, but for now we're focusing on industrial automation. So therefore V increases, W falls. So that's why automation goes exactly on the opposite direction as aging, as you can see. Now on top of it there is the productivity effect, and the productivity effect then shifts this ISO cost out. So in this case, it increases V even more, but I have drawn a case such that even though the productivity effect is very large, it still doesn't take you all the way back to W. But the productivity effect can be large enough that W can increase also. Now, this is the static equilibrium, but what I care about is technology adoption and technology development. So that's pretty straightforward. First, look at the adoption decisions. The adoption decisions are very simple. I'm going to denote theta AI, the adoption margin of industry I. And this equation summarizes it. If the wage of middle-aged workers is high enough, in particular is higher than the cost of robots, which I normalize to PM, you adopt. If not, you don't adopt in industry I. That's that simple. But that immediately shows you that the higher our wages, the more robots you're going to adopt. And we know when wages are higher, when there is aging. When you age, wages are going to increase, so you're going to adopt more robots. So the reason why Germany and South Korea are adopting more robots is because their wages are higher, because their wages of middle-aged workers are higher, precisely because those workers are scarce because of aging. But then there is the next margin, which is the development of technology. It's not only, we'll see this in great detail in the data, it's not only that Germany is adopting more robots, it's actually developing more robots. So I'll be able to show you, pinpoint that very precisely in a second. So let's come to the adoption margin, the development margin. And for that, I just augment this with the simplest formulation of a directed technological change model, where I allow technology monopolists to develop new automation technologies and sell them. And I assume that they do that subject to this cost function. So the more automation you do, the more expensive it is to develop these technologies. That's normal. The only thing I would like to point out here, because I'm going to use it for comparative statics, is this rho I parameter. So the rho I parameter is the elasticity. So if rho I is great, so is large, then that means that the cost of additional automation is not very convex. So you can easily automate. If rho I is very high, is very low, then it's very convex. So I will use data for cross-industry where automation is easy, where automation is hard, and we'll do some comparative statics and both data and empirical on that. Now this framework for directed technological change is actually quite convenient, because when you write the profit function of the firm, it turns out that, and the equations don't matter, but just a basic conclusion matters. So the key word is supermodular. So the profits of technology monopolists is supermodular in theta I and W, which means that under no additional assumptions, the more the wage that you have to pay, the more automation you want to do. And that's very normal. Why? Because automation replaces the middle-aged workers. The more expensive those workers are, the more profitable is automation. So therefore, we can write all of these things taken into account, the equilibrium like this. There is a theta R mapping, which is that we find the best response of technology monopolists for each sector given the middle-age wage. And then that's a function of W, but W itself, from this figure here, is a function of technology. So put that technology as a function of W, and we end up with a fixed point problem. W is a function of the equilibrium through the technology, which is itself a function of W through monopoly behavior of technologists. So this fixed point problem always has a solution. So an equilibrium with endogenous technology always exists. And it looks either like this. This is the case in which automation is strongly labor replacing, which means that when you do automation, you reduce wages. In that case, automation decisions across industries are strategic substitutes. Why? I automate, I reduce the wages, that makes you want to automate less. In that case, there exists a unique equilibrium. Or I automate, but when I automate, the productivity effect is large enough that wages increase in equilibrium. Then there are strategic complementarities. Because I automate, that increases wages, you want to automate, then I want to automate. Then it looks like this. So there could be multiple equilibria. But even if there are multiple equilibria, there's a well-defined least and greatest equilibrium. So either this case or this case, but in both cases, comparative statics are the same. And here they are. In the least and the greatest equilibrium, aging, an increase in phi, always increases the equilibrium wage, always increases automation, and expands the set of industries that adopt technologies. Moreover, the impact of aging on industry automation is more pronounced when alpha I is greater. So what is alpha I? Alpha I is sectors in which there are more production tasks or there are more middle-aged workers. And also it's greater when rho I is greater. What is rho I? Those are the sectors in which automation is more feasible. So all of these predictions we're going to be able to look at in the data. Final prediction, unfortunately it's a bit of a letdown as the prediction goes, is on productivity. Pretty much everything is ambiguous. But it's interesting in and of itself because it says that even though aging puts a negative pressure on productivity, there is no guarantee that productivity is going to be negative. And in particular, automation fights against that. The only non-ambiguous thing, which we'll then be able to look at in the data, is that equilibrium output and productivity increases more in sectors that have high ROI. Meaning that if there is aging, it's the relatively easy to automate sectors whose relative productivity should increase. And that's one prediction that we'll be able to test. Okay, so data. So I'm going to use a lot of data that overlaps with what I've used already, IFR data, but now expanding into 52 countries, so they're going to be developing countries, so we'll be able to look at developing countries. And I'm going to use the same 19 industries in 1993 to 2014, so I'll do look longer period. But IFR is only for robots, but there are hundreds of other automation technologies. So I will be able to get a sense of these by looking at Comtrade data. So the Comtrade data, for those of you who may have seen it, is very detailed imports data. And pretty much all countries in the world import intermediates such as robots, machine tools, automated welding machines, conveyor belts, nanotechnology. So I can look at both for automation and non-automation technologies at a very detailed level. So I'm going to be able to do that. And then I'm also going to look at patents data to look at, again, innovation, both for automation and non-automation. And then I will also look at integrators' location in the US that I already discussed. But first I'm going to start using census, ACS, etc., regular US labor market data to show you some patterns about aging, age composition, etc. So this is one figure that's extremely simple, but you might find it a little surprising. At least I did find it surprising. What I'm doing here is I'm looking at share of employment of workers by different age groups, 20 to 25, 25, 30, etc., etc., in heavily robotized industries. Which are the heavily robotized industries? Those are the ones that you saw in the previous lecture: automotive, electronics, fabricated metal, chemicals and petroleum, shipbuilding and aerospace, etc. So these are the ones where automation, these are the heavy industries where automation, especially robot automation, has been very rapid. And the pattern, and you're going to see a couple of, I think, surprising pictures like this. Well, again, it shouldn't be surprising perhaps, but I don't think it was known before. That's interesting. Is that there is a very distinct age pattern to employment in these industries. So let me focus on just the average, which is the green, or let me just focus the top one, that's the easiest one, 1990. Okay? So it's fairly flat. So the share of workers by age that works in these industries is about 0.8 up to about age 50. And age 50, it starts a very sharp decline, and by about age 65, only about 0.4, half of likelihood of workers being in that industry. So you are much, much less likely to be working in these industries relative to others. This is not retirement. These workers are, this is always being benchmarked to other industries' employment. Why? Because if you're a 64-year-old, 63, in the US, many people in their 60s are still working. You're working in service industries, you're working in retail, you're working in sales, you're working in clerical, you're working in custodial services, but you're not working in these heavy manufacturing industries. But the next picture is perhaps even more surprising. So the same thing, but now I'm doing it not by industry, but by task. So I'm looking at workers in machinist, craft production, and material handling. So the core blue-collar occupations. And I benchmark them to the core service and white-collar jobs. So these are white-collar jobs in manufacturing and then some service occupations. And again, let's look at the 1990 data. About 40%, well, no, it's not 1 divided by others, it's not 40%. About 20% of workers up to their age 50 are in these blue-collar occupations relative to these other occupations. So this doesn't, the denominator here is not all other occupations. I'm leaving out mining, construction, education, etc. But then around age 50, it starts a super steep decline. And again, by the time they're 65, almost no workers are on these blue-collar occupations. So production tasks, especially in these heavy industries, is extremely middle-aged. So if in fact robots are replacing tasks, blue-collar tasks in these industries, they will be highly substitutable to these middle-aged workers, which are of course the ones that are becoming scarce in places like Japan and Germany because of aging. And in fact, we can see that directly. So what I can do is, first, well, this is, I showed you this already, this is that production workers are disappearing in industries that are introducing robots. So I'm using the same variable that I used before, adjusted penetration of robotics, but this figure, I didn't show it exactly, but I showed this to you for employment, but now I'm showing it to you for production employment. And you see that all of the employment patterns, or most of the employment patterns I showed you in the previous lectures because of production workers are disappearing. But this is the one that's interesting. So here, I do exactly the same regression of commuting zone level outcomes on exposure that I did in the previous lecture. But instead of looking at overall wages and overall employment or employment by education group, I look at employment and wages by age. And what you see is that there is the negative effects I was showing you before. They are driven by the middle-aged workers, 30s and 40s. And there is no negative effects on older workers. So indeed, as I was claiming, robots are directly substituting for middle-aged workers and are not much substituting for older workers. So therefore, as in the theory, an overall aging of the population that makes middle-aged workers scarcer is going to induce greater demand for industrial automation and greater development of industrial automation technologies. And so that's what I'm going to try to show you next. So let me start simple, and let me show you regressions of this form. Once I show you these, then I will specialize these a little bit more into a sharper specification where I can worry about causality, etc., a little more. But let me start by robots divided by industry employment. What do I mean by industry employment? So in the denominator, I put manufacturing, mining, and utility. So those are the sectors that adopt robots. So I leave out agriculture, services, etc. So that, and then I have the log population of 21 to 55-year-olds and the 56 plus. And then I have a bunch of controls, and I'll in particular explain what those controls are in a second. Here is the OLS regressions, cross-country and OECD. Actually, so here I'm not showing you the, oh no, I'm showing you the OECD. But let me focus on the cross-country for now. I'll come back to the OECD in a second. So here, no controls whatsoever. Without any controls, you see a negative association between log population of middle age and positive association between the population of older workers and the increase in the stock of robots between 1993 and 2014. You put covariates, doesn't change anything. They're very stable. The one covariate that matters is the baseline robots. Because already there was a divergence and there's no convergence. So in fact, the baseline robots predicts further divergence. That's like Germany starts higher than everybody else and diverges further. That's more common than just Germany. But even though this variable itself matters quite a bit, the pattern is very similar. And the other thing that you see here is that this coefficient is negative, this coefficient is positive. They're more or less the same magnitude. This relationship is going to be fairly robust, especially once I specialize it a little bit more. But in particular, this is not related to GDP per capita, population, average schooling, the initial demographic structure, and also we control for how important manufacturing is throughout, because again, manufacturing may be more robotizable. I will also look at industry level variation in a second that takes out all composition effects more cleanly, but I'm getting there. But this specification suggests that what really matters is the difference between these two things. And so from now on, I'm going to specialize this to this simpler thing, which is change in the stock of robots. On the right-hand side, I have aging, which is the change between 1990, and I project it into the future. It doesn't really matter, but this is theoretically more satisfactory because robots are very forward-looking investments. Especially they have they depreciate about 15 to 20 years, so 2025 is a good time to extend it to. It's the ratio of older workers to middle-aged workers. So here are those estimates. So again, no covariates. This one aging variable very strongly correlated with the adoption of robots, and by itself accounts for about 50% of the variation in cross-country adoption of robots. So, in fact, within the OECD, it's even more. So, about half of all variation that you see is just due to aging. And if you do just the partial R-square in these specifications, it's nowhere less than 40%. So aging has a huge correlational power, and I'll try to argue that it's causal in a second. Now put the country covariates, GDP, population, manufacturing, etc. Very little change. Put initial robots, again, as I show you, that matters, but it doesn't change this coefficient much. This is the OECD. Same relationship, very similar between the OECD and non-OECD. But it's really interesting because the developing countries are following exactly the same pattern, non-OECD countries. So let me show you things in a graph. Here is on the left-hand side the whole sample, on the right-hand side the OECD. You see that everything lines up along the line, and you see why there is a 50% R-square. But one outlier is notable, and that's Korea. As I showed you, South Korea adopted so fast that in fact they over-adopted even despite their very rapid aging. But all of the analysis is done in the paper with and without South Korea, and it doesn't change anything. And you can see that because take out South Korea, still the countries line up along a straight line. What does this mean quantitatively? So if you have a 20 percentage point faster increase in aging, that's the difference between Germany and the US, that leads to about 0.14 robots per thousand per each year, or 3 more robots during our sample period. That's about 30% of the difference in robots adoption between Germany and the US. So those are the ballpark numbers that are going to recur for many other contexts, with many other technologies. About 50% in an R-square sense, about 30% of the difference between Germany and the US, between 30 and 40 in general. So quantitatively, these are very large effects. So aging is really first order if you want to think about automation. That's the basic thing. But of course, these regressions are just correlations. But why would aging be endogenous? Well, the main reason is immigration or outmigration. Germany has been open to immigration much more than any other European country for a very simple reason, because they've had a shortage of manual laborers for the last 40 years. It's the same story for Germany. So even before the demographic change kicked in full. That's why they've been importing workers from immigrants from south of Europe and other parts of the world for so many years. So that would mean that aging variable is endogenous for Germany. But there's a very simple solution to that. If you use fertility rates going back to the 1940s, under the plausible assumption that fertility rates from then were not anticipating the future robotics technology, that's a good source of variation. It purges all of the out-migration, in-migration type things. So that's what we do here. And these are the IV estimates, exactly the same specification. And you see the IV estimates are equally precise, just slightly larger in the baseline, but when you put the covariates, it's very, very similar. So quantitatively, the IV estimates give you exactly the same 40%, 30% quantitative results. Now, this is all the long difference specification, and as I've told you in the context of the robots and jobs paper, long differences is clean and it's very easy to think through, but it doesn't use the timing. There I was talking about the timing of exposure to robots, but here the timing of aging. Remember, Germany ages early, South Korea ages late. So I should really be using that timing, and I'm not using it. So again, same strategy. Let me do stack differences. Oh, so just forget about that. That's not important. So this is the stack differences. I'll come back to that. It's not, well, since I put it in there, but I thought the order was reversed. So here is a stack differences specification. You have two sub-periods from 1993 to 2005, from 2005 to 2014. And you see same pattern both in the OLS and IV, but the really interesting results are these columns here, where we are putting, again, country linear trends. So these are very demanding specifications that say, are you adopting the robots precisely in the decade in which you're aging and not in the other decade? And the answer is yes, and actually the coefficients are very similar. In the OLS, they're very, very similar. In the IV, a little bit larger than the long difference specifications. Now, one other thing that you might worry about, just like the pre-trends thing that I discussed in the context of robots and jobs, is that perhaps these countries were on different trends. One way of looking at that is to see whether past aging predicts robot adoption. Past aging shouldn't matter conditional on the current age structure, and that's exactly what we find. Past aging has never got any effect. So it really looks like the right timing and the right type of response to aging. But the next question is this just about robot adoption? Or is it really about automation? And is it really about also innovation and the development of robotics technologies as well as adoption? So to do that, I'm going to first look at the Comtrade data. So in the Comtrade data, you can very clearly identify industrial robotics and components. So what we do is we take those and we divide your total imports of robotics components by your total intermediate imports. We're not interested if countries with different age structures import more or export more. So everything is normalized by that. And then for these import specifications, we leave out Germany and Japan, which are the major robots producers in the world. So this is the relationship. Aging countries, OECD or the whole world, imports much more robots. And if you do the quantitative magnitudes, it's the same thing. About 40% of the R-square variation and about 30 to 40% of the quantitative gap between the US and Germany. But this is just a check on our IFR data, or really the IFR data, which is higher quality, is a check on this data, which sort of suggests that it passed. Now, once we do this, we can look at other intermediates, other technologies. So here they are. So the nice thing here is that I can start with things that shouldn't really be responsive to aging. Computers, other industrial machinery, agricultural machinery, and those are not related to aging. I'm just showing you the coefficient estimates for full sample and the OECD sample. Moreover, I can look at machine tools that are not automated. So I can look at manual machine tools, manual welding machines, tool for industrial work, non-numerically controlled machines, conveyors, and those are all 0. But now look at the automated machinery, dedicated machinery, numerical control machinery, weaving and knitting machines, textile automation, automatic machine tools, automated conveyors, and all of those are positive. So meaning that all automated technologies are imported more when you're aging, again, because they are all substituting for the middle-aged workers that are becoming scarcer. But even more interesting, in my opinion, is that once we have this Comtrade data, we can look at your exports of robots and exports of other types of automated machinery. So in a world in which technologies are produced for your domestic market, which was my theory. Actually, the theory that I presented was simplified. It's also embedded in an international trade setting, but I didn't present that. But it's a model in which you produce, develop technologies first for your domestic market, and next you can sell them. So in a world like that, if you're aging, you should also be selling to the world more of these automated machinery. So that's exactly what we find. So now I'm doing exactly the same thing, but now exports of your robot components divided by your total intermediate exports. The more you age, the more robots you export. And that's again true for OECD and for the whole world. Then this is now no longer no longer just a validation of my IFR data, because it's looking at exports, not use. Now, of course, some of the exports is secondhand, etc., so there might be some correlation. So that's why I'm going to look at a more directed, more specific patent-based measure of innovation, but it already is suggesting that these countries are not just using more robots, but they're developing and selling to the world more robots. But once I have this measure, now I can do this for other automation technologies. And here they are, exactly the same list here. You don't sell more computers, you don't sell more agricultural machinery, you don't sell more conveyors, none of the more manual tools, but most of the automated machinery you sell more. Dedicated machinery, numerical control machinery, automatic welding machine, weaving and knitting machines, and other textile dedicated machinery. So it's a general industrial automation. But as I said, what you might want to do is focus more on patents or on innovation. So here, what we do is we create several measures of automation and robotics patents, doing abstract keyword and text searches from the USPTO patents data. And then we normalize everything by the total number of patents. Again, we don't want to, Finland's patents are those that are patented in the US by Finnish companies or Finnish innovators, and then the denominator is all Finnish patents, again, in the USPTO. And then we do the same thing, the relationship with aging. So here I'm showing you the robotics patterns, and I'll show you some other ones in a second. So same pattern. The more you age, the more robotics patents you take out. The more you age, the more robotics patents you take out. This is OECD, this is the full sample. Again, the quantitative magnitude is about 30% of the US-Germany difference and about 40-45% of the OLS, of the R-square. Now let's look at more specific measures. So this is robots. This is some other classification of robots. So these are other words related to manipulators and robots, words related to broader class of robots, and all of those give the same results. But interestingly, you have no similar relationship, as I was anticipating, with computers, nanotechnology, biotechnology, pharmaceuticals, software, etc. So it's really unique to automation technologies and industrial robots that aging countries are specializing in terms of production, in terms of innovation, and in terms of use. This is all cross-country, and I've done, my best, but it's limited, to make these countries comparable by controlling for industrial structure, education, demographics, GDP, but it's still cross-country. So it would be useful if we could show the same thing, comparing more like apples and apples. So one thing is, again, go back to the US and look at commuting zones, and do the same with these integrators data that I described from Lee, Green, and Kraft. So here is the same thing. Now I put the integrators on the left-hand side, aging on the right-hand side. Now on the right-hand side, I can control for much more detailed demographics, the same things, education by 5 education bins, age structure, and I can control for industrial structure in a very detailed manner, which we do. But importantly, here you shouldn't really look at the OLS. It sort of works with the OLS, which is surprising, but you should look at the IV because migration is a much bigger deal. And in fact, it works with the OLS, but the coefficients are different, as you should have expected. Here it is visually. On the left-hand side, you see where the integrators are. This is something I could have shown you before in the context of the robots and jobs, but I didn't, but I'm showing it to you now. So you see this is the industrial heartland where the robot integrators are. And this is another area which has heavy industry. And these are the aging areas. You see, actually, this area here is not very heavy industry, but it's still adopting a lot of robots because it's aging very rapidly. And here is a bin scatter plot of the data and the positive relationship. So I can't show you the whole data because it becomes too much of a cloud with 722 commuting zones. And here is a regression version of it. So when you control for everything, that's the specification here. You see still a fairly precisely estimated about a t-c statistic of 4 effect. That's, again, in terms of quantitative magnitude, quite large. Now, the next thing I want to do is move on to the cross-industry predictions. So now I pool across industries. So I go not to the country level, but the industry level. Now, the industry level, you have to be a little careful because there's more missing data. So I do this at the annual frequency and then cluster the standard errors at the country level so that serial correlation is taken care of. You could do it at the stock level, but you lose too many observations. And then, other than that, the covariates, you can still include covariates, but you don't need to because now we can include many of these things directly because we are controlling for industry structure. So in particular, there are always industry fixed effects. So this is asking within a given industry, are you adopting more? But more interestingly, now we can look at the 2 other predictions from the theory. Are industries that rely more on middle-aged countries adopting more robots when they age? That's very important because you remember the channel, the mechanism is you adopt the robots because you have a shortage of a crucial factor of production, middle-aged workers. So it should really fall on industries where these middle-aged workers are important. If you were employing like 1% middle-aged workers, who cares about that scarcity? You just pay them a little bit more, that's it. But if you're employing 50% middle-aged workers, like on the production line, that's a big deal. And then this one here is opportunities for automation, and we use a number of different measures. We either use the replaceability index of Greats and Michaels, which looks at the occupational structure, or a dummy variable for industries highlighted by the Boston Consulting Group's report on the future of automation. And here are the results. I'm just showing you the IV, but the OLS are very similar. This is the same as the cross-country effect, but actually is a little bit larger, which reflects that actually when you do industry composition adjustment, which this regression directly does because you're looking at industry by industry, the effects are actually slightly larger. But the important things are these interactions. So the aging interaction here is very precise and large, and the aging interaction with opportunities for automation is also very large. In fact, quantitatively, what these effects show is, is that essentially no additional change. If you look at industries at the bottom, say at the bottom 10 or 25th percentile of both middle-aged worker use and opportunities for automation. There is no effect from aging. Those industries are not doing any differential robot adoption. The effect is all being driven by industries at the top end of the middle age distribution and the top end of the opportunities for automation distribution. And then the final prediction, as I highlighted, was on productivity. I wish I could do more on productivity. And we're thinking of new approaches for productivity in the future, for future work. But for now, all I'm going to do is run a similar regression, but with productivity on the left-hand side. Actually, I'm not going to put productivity on the left-hand side. I'm going to do something more demanding. I'm going to just put log value added on the left-hand side. Why? Well, because productivity is value added divided by labor. But I'm showing you that this has an effect on labor already. I showed you that in the cross-industry things. So I'm just looking at value added, which is even stronger. And here is the results. There is no longer any effects of having more middle-aged workers for a very good reason. If you rely more on middle-aged workers and there is aging, scarcity of middle-aged workers is a direct bad for you. But interestingly, that's generally not always significant because it's being counterbalanced by automation. But more importantly, industries that are providing more room for automation, their productivity explodes in aging countries. So this is why Germany and South Korea and Japan are not doing that badly since the 1990s, because their automation has increased their productivities in these heavy industries. And then the labor share, let me not show that since I have highlighted that. So, what does this imply for the future of work? So, remember we started with the debate on whether we should just say technology always helps labor and we shouldn't worry about technological trends. That's one pole. The other pole, well, the future is very bleak for labor because these brilliant, amazing AI things that Ray Kurzweil talking about, we're going to do all the jobs and there's going to be nothing left for labor. Actually, by the end of these 3 lectures, I hope a more nuanced and richer framework has emerged. First of all, we cannot and we should not think of technology just like a blob that just in a black box manner helps or doesn't help or whatever labor. It's really about this task structure. And when you think of this task structure, it also becomes clear that at least any of the technologies that have so far been used, and I would say the same, we can talk about this a little bit more perhaps in the question and answer, about technologies that have been invented so far, none of them have any capability to do all of the tasks or even close to all of the tasks that humans do. So we're talking about a subset of tasks. For industrial workers, those blue-collar production tasks that I mentioned and I showed you the robots replacing on the factory floor. So therefore, automation has the capability of replacing some work, but it's not going to be the end of work. But also equally, overall knowledge that we are generating, say AI or digital technology platforms, can be used in many different ways and can be used with many different levels of productivity. And those provide a menu of possibilities to societies and to firms. And I've emphasized one aspect of that with the new tasks and reinstatement in the first lecture. That is extremely valid, but now we're seeing another menu, or another choice in the menu, which is that you will use automation, but you will use automation precisely when scarcity makes it very appealing to do. So, in particular, what we are seeing here is that automation in countries such as Germany and Japan, far from being a negative force towards productivity or employment, have actually helped productivity and helped prosperity to an appreciable degree, because they have helped produce tasks that would not have been feasible to perform given the changing demographic structure. Now, at this point, you might think, well, isn't there a bit of a contradiction in what you heard in the first lecture, or actually even the second lecture, and right now? Because in the first and the second lecture, I've told you you can automate, and that might reduce labor demand, it might reduce employment. And now I'm saying, actually, these things have helped labor demand. Why am I saying that? Well, actually, there's no contradiction. And there's no contradiction, and it's a little subtle, but once we understand it, I think we're going to get a much better insight about the future of work. And for that, I will go back to the theory. Let me focus on this one, but the same thing happens when there are multiple equilibria. So this is here what happens to the equilibrium when there is aging. When there is aging, you automate more, but the wage necessarily goes up. Theorem. When automation is induced by aging, labor demand always goes up. So how do we square this with my previous result that labor demand can go down? Well, because there I was looking for an arbitrary change in automation. So for an arbitrary change in automation, meaning that I just automate out of the blue, or for example, because Germany invented an automation and it spreads to me, there the productivity effect can be outweighed by the displacement effect. That's this example. An arbitrary automation, look, wage goes down. But when it's induced in equilibrium for a country that is at the equilibrium point, it always helps labor demand. Why is that? The difference, and this is going to tie it to institutions, is about wages. When you are automating because of induced wage effects, wages are high. When wages are high, that means the productivity effect is large, because the productivity effect is the cost saving because you're substituting machines for labor. And that large productivity effect ensures that labor demand goes up. But if suddenly you plop up an automation technology on me when I didn't have any need for it, I may have very low wages, especially if labor market institutions like in the United States are not protecting labor. But if I replace very low wage workers with automation, then I don't get much productivity gain. Then that actually further reduces wages. So therefore, if automation is being done in the right institutional environment, and because there is need for it, as there is in an aging world, it can actually not just increase value added, which we have seen multiple times it's doing, but it can increase it in such a way that it undoes the negative effects of displacement, and it increases labor demand also. So therefore, we're coming back to the same picture. We have a technological platform, technological capabilities. But it's a question of how we use it. If we use automation when there is more need for it, then we get bigger productivity gains and we get better prosperity results and not so many of the negative effects of automation. Second, when we do it not just for automation, but also for new tasks, then we have much better chance of generating productivity growth. And here is the US data on new tasks. So even though I have been complaining in the first lecture that US hasn't done enough in terms of new task creation, and if you look at the current 20-year period relative to before, there is much less reinstatement. Despite all of that, about half of US employment over the last 30 years has been generated in occupations in which there are new tasks and new job activities. So on the horizontal axis, I have share of new job titles, and on the vertical axis is percent change in employment growth in that occupation. And you see the occupations that are growing fastest are those that have almost completely new things. So if you project this and do the calculation, about half of employment growth is accounted for by just new tasks in the US. So there is therefore quite a lot of room for doing new tasks. It's just a choice of the society whether to do it or not. And when it's done, which means different type of innovation, different types of policies, especially whether you treat capital special, which encourages innovation, which encourages automation and which might lead to excessive automation, and whether you just create just excitement about labor replacing AI or automation, or a more broad-based approach to innovation, I think has first-order implications. And again, I want to end by emphasizing the importance of institutional environment and the overall change in the industrial structure and technology, going back to mechanization of agriculture. So during this period, the reason why the US prosperity continued to grow isn't because agriculture was doing so well. This is what happened to labor share of agriculture. Employment in agriculture falls similarly. But it's because labor share in industry increased and industry itself expanded. And that's again about reorganizing, reconfiguring technology more broadly. So imagine that you go back to the end of the 19th century and the beginning of the 20th century. And imagine that you create a counterfactual US economy where you have exactly the same behavior of agriculture, but no change in industry. What would happen? We would not have had 1/3 of the productivity gains that the US economy had during that time, and we would have had mass unemployment. So if we use as a US economy or as European economy, all technologies just for automation, I think the risk is doing the same, which is that you leave a lot of low-hanging fruit. So finding the right way of using these technologies and doing the automation when the need for it is greater, like in aging workforces, I think creates a much more optimistic read for the future, but it's also for something that will require institutional adjustments. So this adjustment here would not have been feasible, for example, as you pointed out, without the mass schooling movement that just fortuitously happened at the same time. So there was an explosion of people with high school degrees. Unfortunately, none of these workers who were losing their jobs in agriculture went into clerical jobs, because they just did not have the education level. But the next generation had the education level and they could go in. So the institutional environment for that is very important. Institutional environment for protection of workers is very important, but also policy is very important. So for example, the US, just like OECD countries, but even more, treats capital so much more favorably, and over the last 3 years it has come to do so much more. So as a result, what you're going to have is that even when it makes no economic efficiency sense for firms, They will be very profitable for them to automate because you get a lot of subsidies. But that is exactly in the wrong direction, which means you're going to excessively automate. You're not going to create a demand for finding new technological solutions that will increase labor productivity, new tasks. So any conditional optimism about the future of work has to be conditioned on institutions improving, which of course is a tall order, but that's a topic for another lecture. Thank you. And now we have a little bit more time for questions. Seppo has one. Terry? Seppo is gone.
Sorry, maybe I can talk without the microphone. Well, could you continue a little bit more on this closing line about what you basically the idea is obviously the question of automation. There is some adjustment for labor conditions where policy might be helpful. But what about the new tasks? And what kind of policies should countries think about to improve? Then clearly that's the point. If you get new tasks, new innovations, that is a big bonus according to the analysis.
Absolutely.
So.
Well, let me give you two answers. But after saying I don't know. The first answer is that once you can start measuring something, you can start controlling it. So new tasks is a relatively new idea, and we are very much in its infancy in measurement. But imagine that we were sitting here in 1970, and we had the same conversation about green technologies. Well, we didn't have good measurement for green technologies at the time, so it would have been very difficult for us to say, well, can the government encourage green technologies at the expense of less green technologies? But, over the previous 30 years, European governments, even the US government, thanks to state governments, but also subsidies from the federal government, has done a fantastic job of supporting green technologies that many of them have come to the same level of cost effectiveness as oil and coal. Unfortunately, not shale gas. But if there wasn't shale gas now, green technologies would be quite competitive. So I think I start from the following proposition, which is that we know from basic economics that innovation done by a market is not efficient. And it's not just the quantity of innovation, but the direction of innovation. So that means that there is room for the government in some limited ways to affect the direction of innovation. And that's what climate-friendly technologies and the subsidies for them have done. To the same extent, especially in an environment where tech world is dominated by Facebook, Google, Netflix, Amazon, if the emphasis is too much towards certain uses of AI and automation, support for basic research once we start measuring what we want better is actually not completely crazy. But I will give you a simpler answer, is that if in fact I am right that our tax policies are already distorting things, even before you go there, correcting the tax distortions would also achieve a lot of that. So imagine the following thought experiments, very simple. Imagine that you can produce for the next 20 years some of your output by hiring 20 workers and you're going to pay them $10 million. And imagine I give you a machine that will do the same thing for $15 million. That's much, much worse. But given the US tax code, you would be more profitable doing the latter. So which means that it's crazy for any innovator to develop things that work with labor, because just firms are not going to find it, because the tax code is so aggressive in supporting capital. Capital gains are not taxed. Amortizement means you get a huge investment credit. If you do debt financing, you actually can write off a lot of it with additional tax credits. You don't have to pay employee contributions. You don't have to pay healthcare. You don't have to pay all of these additional costs that you have to deal with, and you don't have to deal with workers, which, you know, many of the people who are leading the technology world think is actually a very bad thing to deal with workers. So all of these creates a huge bias against labor. So if you start removing that, the market might actually do more in terms of these new tasks.
Thank you. And there was one question over there. Yeah.
So it seems to me like the creation of new tasks has been relied on the fact that humans perform certain tasks like cognitive and creative tasks. They just perform them and machines can't do that. But this doesn't need to be inevitable, right? Because given the developments of artificial intelligence, we might see a future where the subset of tasks that are exclusive to humans might converge to zero. So what would that kind of future look like, and how does the things that we've been talking about?
That's a great question. Thank you for asking it. And if I had time, I would have talked about it, but I was hoping somebody would ask it. So that perspective is exactly what you'll hear from most, but not all AI researchers in Silicon Valley. And I think I disagree with it for two reasons. The first one is that even if machines are capable of performing all the tasks that humans do, that still doesn't mean that room for humans disappears. Because think of, I don't have the graph here, but the graph from the first lecture where I had the task space. Think of that like a treadmill. First you introduce a task and humans perform it. And over time you understand that task, whether you collect data, and at some point machines perform it. So even though all tasks may be ultimately performed by machines, still, it may take time for machines to get there. So many of the tasks that today machines cannot perform, in 20 years' time they will start performing, or 30 years' time. But in the meantime, we will have introduced new tasks that will be completely new, and the data or the architecture will not be there. So that's the more modest answer. But actually, I believe something even stronger than that, which is that I think despite the experts, but the experts always look at the world through their blinders, I think there is a limit to what machines can do, at least in the next 100 years. And that's that a lot of human tasks have a degree of creativity in them. And machines, despite the fact that some people talk of artificial general intelligence, have no creativity. It's all based on finding more data and realizing patterns internally. Whereas a lot of human intelligence, which actually is used in a lot of tasks, is extrapolation and analogy based for things for which you do not have exact data. Now, is it possible for machines to do that? I don't know the answer. So early cybernetics research, people like Simon and some computer scientists like Minsky and Wiener thought that it was, and that you could build machines that thought exactly like humans. That's turned out to be a fool's errand. And the new AI research made a conscious decision to move away from that and not try to replicate human intelligence for doing data-based, unstructured data-based replication of very specific narrow tasks. And even what goes on under the name of artificial general intelligence now is that. And I think that really doesn't provide any room for doing creative tasks. Now, will a new research paradigm emerge in 50 years and then in another 50 years really start replicating human brains? It's hard to know, but I'm quite doubtful.
Okay. Thanks, Eddie.
Yeah, so my question is about like how will this affect the global inequality or like robotization? What will happen to the third world and the countries that are really underdeveloped? So will this solve any big problems like global hunger or like the 600 million people that are really ostracized? Or I guess or is the robotization mostly like happening in the Western countries and developed countries, or will this have a potential to somehow like make the income gap smaller between the poor and rich countries?
I don't know. I think, again, it's a question of how you use technology. So I mentioned it in passing, but artificial intelligence combined with robotics has huge potential to be used in agriculture. And if you look at the poor world, for example, agriculture is the one sector where productivity is the lowest. It has huge potential for public sector delivery. And if you look at the developing world, public sector issues, health, education, are huge problems. So there are certainly uses of this technology that could be helpful. But again, I think business as usual scenario, the opposite. And the reason for that is that, caricaturizing it a little bit, but a particularly salient development strategy of the last 70 years, for example, as pursued by South Korea, Taiwan, and more recently by China, is use your cheap labor together with export orientation to start at the lowest end of the manufacturing value chain, then move up the value chain by learning by doing and technology imports or technology stealing in the case of China. But whatever it is, that technology upgrading path has been very, very successful. Now, with automation more broadly, but robots especially, that path is going to become closed to many countries. And in fact, you're seeing that already, that many tasks that were previously offshored are being reshored. One place that's suffering the consequence of that is Mexico. So Mexican manufacturing, especially in the northern Mexico, used to do a lot of the lower end of the value chain auto parts for U.S. manufacturing, especially for U.S. manufacturing in places like Tennessee and Alabama, the South auto suppliers. But you can see, you can put on the left-hand side of, not this regression, but a similar regression, Mexican employment, and it's negative. Meaning that when there is more automation in the US, in industries which Mexico used to offshore or used to the parts of, Mexican employment is declining. And that's because those jobs are now dying by, not by Mexican workers, but by robots. So that's really bad news for Mexico, and more broadly, it's bad news for the next South Korea, next China. So the room for this rapid development being shut off means that the global inequality trends might be quite different in the future.
Thank you very much for all the questions, and especially thank you, Professor Daron Acemoglu, for these excellent lectures.
Thank you, my pleasure. Thank you.
Let me thank you once again on behalf of the Janssen Foundation. It's been a great day, and we are very happy to have been enlightened from the frontier research. Let me return back to the table where I showed in the beginning, the first lecture, showing the list of the Janssen lecturers over the years. 21 lecturers, 10 Nobel Prizes, and the average period from the date of lecture to the Nobel Prize was some 7-8 years. So, according to this, I can make a statistical inference that if you have 50% chance to obtain the Nobel Prize within 7-8 years. Thank you.